So today I'd like to tell you about one particular way of doing probabilistic programming in Haskell with monads. And of course, this has been done before. I'll talk a bit about related work later on. But all the approaches I have seen so far for doing probabilistic programming with monads aim to perform inference exactly by enumerating all the possible outcomes. And while this works fine for small problems, it is not really practical for larger problems, such as those that can be encountered in machine learning applications. So what I'm going to talk about today is another implementation of probability monads in Haskell that uses some of the popular sampling algorithms to perform inference more efficiently. So let me start by saying that, well, to my knowledge, there were two different communities that made significant efforts towards building probabilistic programming systems. And one is the programming languages community, which is who we are a part of, and the other one is the statistics community. And even though I like to count myself among the programming languages people, I really work in machine learning, which is much closer to statistics. So let me tell you about why we think probabilistic programming is important. I represent a Bayesian view of machine learning. And roughly what that means is that when we build a model of something, we specify the entire process of everything that's going on. And basically, to the best of your knowledge, you write a computational process that simulates how the world works. And whatever you don't know, you fill out with probability distributions. And this is the only part that is arbitrary in Bayesian modeling. Once you write your model, everything follows from the observations that you see. So you have some data, and if you want to make predictions from the data, you just apply the Bayes rule, and everything follows from that. There is no more room for any ambiguity there. So it all works very well in theory, but unfortunately in practice, the task of computing the conditional probabilities for Bayesian inference is computationally very intensive. And hence, in practice, we need to resort to approximate inference algorithms. And this is a major drawback of Bayesian methods, because even though those algorithms are quite powerful, they are difficult to implement and even more difficult to debug. And that basically means that a lot of Bayesian methods are inaccessible for people who aren't experts in the field. So what we're really trying to do is have some sort of formal description language. You can think of it as a DSL for probabilistic models, where you specify your model, and once this is done, the inference is performed efficiently for you. So that's the goal. Let me tell you about what we'd like to have in Haskell as an implementation of such probability distributions. So we'd like to have a data type dist, such that dist A encodes distributions over values of type A, and A can be any type whatsoever. It can be an integer, a real, a function type, another dist, anything goes. In order to construct distributions, we'd like to have some sort of primitives for the standard distributions that are widely used, such as normal or Bernoulli. Bernoulli is basically a flip of a biased coin. So the argument to Bernoulli tells you the probability of getting true, and with 1 minus that, you get false. Then there's a categorical distribution, which is basically a list of weighted values, and a uniform, which is like categorical, but they all have the same values. Okay. Aside from those primitives, we'd like to have a monad instance for this, and that allows us to compose them in arbitrary ways. And something that allows us to actually observe data and condition the distribution. So if you take a look at the definition of the condition operation, so it takes a function from A to prob. Prob is basically a non-negative number representing a probability or probability density. And For those of you who know a bit about Bayesian methods, this part is sometimes, well, it's called the likelihood. And essentially, it tells us how we should reweigh all the different outcomes. Perhaps this will be a bit easier to understand with examples. But basically, what we have is the likelihood, and then the first argument is a so-called prior, which is the distribution over things where we haven't observed any data yet, and what we get back is the posterior. So the distribution, the distribution describing your final beliefs about the system. Okay, and how we're going to get something back from the distribution. In this talk, I'll only use sampling methods for inference. So the only way to get something back will be the sample function, which takes a random number generator and a distribution, and it gives you back a value. Okay, so having this interface, how do we actually write models? What I'm showing you here is a very simple example of linear regression. So you can think you have a number of points in 2 dimensions. Each point has an x and y value, and you're trying to find a straight line that best fits the data. So the model will be, the type of the model is a distribution over functions from a double to a double. Note that this is not a distribution over parameters of linear regression, but rather a distribution over functions. And I only did it to demonstrate that this approach can be used in a higher order manner. So you can actually define a distribution over functions, even though those are just linear functions. So there is no restriction that says you must write a distribution over tuples of doubles. And, well, the way this model is defined is basically we sample a first coefficient, the slope, from a prior, which is a normal distribution, and the intercept from a normal, and we return a linear function. So that's relatively easy. And how do we do conditioning? This is a, well, maybe slightly tricky part. So in order to do conditioning, well, we take the prior distribution and a point that we want to observe. And basically what the function observe1 does is uses the conditioning operation. And the part that you see here is the noise process. Because in order to make any sort of regression, we need to assume that our observations are noisy. So here we just have a normally distributed noise that centers around the value of a function at point x and has a standard deviation of 1. And we observe the value y from it. PDF stands for a probability density function. And with a function to observe one data point, we can just perform a fold over the data to get all the data points. Okay, so a slightly more involved example is a hidden Markov model. And this is usually depicted in this way, where we have a sequence of latent random variables, those that we can't observe. And there is a sequence of observable variables. In our example, each of those latent variables, we have one of 3 values, -1, 0, and 1. And the observable values will be real numbers being noisy copies of the latent values. And the way this model works is that every state only begins on the previous one, and the transition probabilities are defined by a probabilistic finite state machine, as you can see here. So how do we actually encode it? So the easiest way to read it is basically what we perform is a fold over all the data points. So values represents our observed data points. Start is the starting distribution, and well, it is a distribution over the first latent state. And expand function basically enlarges the HMM by 1. So what this does is takes what has been generated so far, performs the transition on the first element. Well, on the last element that is actually the head of the list. And then it returns the new element attached to the old list. And finally, it performs conditioning by applying the score function to the head of the new list. And the score function is defined by simply a normal noise as before. Okay? And this is the transition model as defined on the previous slide. And okay, so those were some examples. Now, the point that I'd like to emphasize here is those are really just very simple models that I showed you as some demonstration of what can be done. In practice, if you actually wanted to use those models, you probably wouldn't go with a general purpose probabilistic programming package, but rather use some sort of specialized library for dealing with HMMs or linear regressions. So bear in mind that this is just an illustration. In practice, we would be interested in more involved models. Okay, so let me tell you a bit about how we actually implement this. So we use a GADT as a representation, and this is a rather simple GADT that you may identify as a free monad. So basically, the constructors correspond directly to all the operations that we can perform on a disk. For primitive, we can take anything that can be sampled from, and this is quite a flexible solution because it allows you to import all the functions from standard libraries that define sampling methods, and also if you want to define your own custom distribution, you can also easily make it an instance of sampleable and put it there. Okay, and as I said, the way we're going to obtain values from a distribution is by sampling from it. So recall that sample takes a random number generator and a dist, and most of this is relatively straightforward. The only interesting clause, or maybe there are two interesting points. One is that rather than threading the random number generator throughout the computation, we just split it every time the bind is performed. And this is mostly so that the resulting implementation of sample is actually lazy. But the more important point is that sampling from a conditional distribution is undefined. And the reason for that is that conditioning is really a declarative operation. It doesn't tell you how to sample. It only describes the distribution. And, one of the main points here is that the way we're going to see inference in this framework, even though we're using randomized inference algorithms that will perform some random choices themselves, we will not actually mention any random number generators anywhere outside the sample functions. Any inference method should be a deterministic transformation that takes a dist and returns an equivalent or an approximately equivalent dist that doesn't have conditionals anymore, and so it can be sampled from. I'll show you some examples in a minute. Okay, one thing I should mention is that in what follows, we will assume that all conditionals are known statically, and that means that wherever we have a bind, the conditionals can only be on the left of the bind and not here on the right. I won't go into details about that. There is some discussion of this restriction in the paper. It's not necessary, but it makes implementation of the following inference algorithms easier. Okay, so the very, very basic thing that you could do and call it inference is just sample from the prior. That basically means discard all your data and, do what you would if you haven't seen them. This is here just for completeness. But a slightly more involved thing that you could do is not only, still sample from the prior, but also return the likelihood score. And what this means is that every time we encounter a conditional, we will just update the accumulator. So you can think of it as a weight of an execution trace. So what we obtain is a distribution over values and associated weights. And the idea is that if we were able to somehow integrate over that, at the end we would get the right distribution. And the reason this is useful is we can define the Metropolis-Hastings algorithm on top of that. So this is a very simple version of Metropolis-Hastings, which is perhaps not that practical, but, well, it's nice because it fits on one slide, and it actually will be useful later on. What it does is take a distribution, and it gives you back not a single sample, but a chain of samples here, really an infinite chain of samples. And there are some results that can be used to show that if you get sufficiently far up the chain, then you get good samples. At the beginning, they're bad samples. Later on, they're good samples. And what you do in practice is discard first 100 or 1,000 samples and stick with how many you want later on. Okay, I'm short on time, so I won't discuss the implementation of that. And okay, so there is the Metropolis-Hastings algorithm, and there is a sequential Monte Carlo algorithm, which again I'd love to tell you about, but we don't have time for that. So I'll just say that it takes a parameter, which is the number of so-called particles. So say this is n, then SMC runs n copies of the program, and there is some magic happening there about how different copies are killed or duplicated in the process. But the important point is that it gives you a distribution over weighted samples. And if we pick one particular sample at the end, we get a transformation from a disk to a disk. And the reason I think it's exciting is we can actually use it to compose different inference algorithms. So this is perhaps the most important result from the paper. There is this recently proposed algorithm called the particle-independent Metropolis-Hastings. And really what it is a Metropolis-Hastings algorithm that uses SMC for proposing values for the Markov chain. And what I really like about our framework is that we can actually literally compose SMC function with MH function to obtain a new inference algorithm and avoid all the pain associated with implementing PIMH from scratch. Okay, so there's just a brief mention about performance. So the particle independent Metropolis-Hastings algorithm and SMC were applied in the context of probabilistic programming before, originally in a system called Anglican and later in probabilistic C. But they're not implementing things this way. So really what I'm showing here is just the demonstration that we achieve comparable performance. And those lines are in log-log scale. This is the KL divergence versus the number of samples. And basically, you probably can't see that, can you? But if the sampler is correct, there should be straight lines with a negative slope. So I hope that, no, I'm not sure even if you can even see that much. Just take my word for it, they're straight. Okay, let me just briefly mention that we also have a notion of formal semantics for this. And this is an old trick that I've seen in many places before. So unfortunately, I cannot credit whoever first thought of that. But the idea is to view a distribution as a function from a random source. And this is a finite tape of random numbers, or finite tape of real numbers between 0 and 1. And what we get is value and weight, and then the remaining part of the unused part of the tape. And the reason it's wrapped in a maybe is because we can potentially run out of tape. So if the tape is sufficiently long, that's good, we get a value, otherwise we get nothing. And we can actually use it to define semantics of distributions in terms of measure theory. So there are some technical problems here that I will not discuss. But for sufficiently simple types, we can define formal semantics in terms of measure theory. Okay, so let me just briefly discuss the related work. So the first implementation I've seen of probability monads in Haskell was the work of Erwig and Kollmansberger, which, you may have seen before, and basically they implement the distributions as finite lists of values and associated weights. But the problem with that is that this list grows very big very quickly. Okay, there's another piece of work by Ken Larson, which was sadly never published, that offers a more memory-efficient implementation in terms of, GADT, that provided inspirations for my own work. And I think I should stop now. So let me just tell you that, the inference algorithms that you've seen here will first appear in a system called Anglican that was designed by Frank Wood and collaborators. And one final point is that our code is available on GitHub, so please take a look and let me know what you think about that. Thank you.
Could you go back to the slide where you showed the performance comparison? So I'm curious if you did the same sort of comparison with more data points, the table below. And I asked this because just sort of squinting at it, it looks like you might have different asymptotics than Anglican or probabilistic C. Well, actually, who knows about probabilistic C? Than Anglican, since it seems that the Haskell implementation is faster for small problem sets, yet ends up being slower for the biggest ones. But with only 3 data points, it's hard for me to tell.
Okay, that is indeed a correct observation. We have different asymptotic behavior. Although what you see in the table, this is not a number of data points. This is a number of particles that you use in the sequential.
Sorry, I meant more data points in terms of trying more different numbers of particles.
Okay, so indeed we have different asymptotics, and the reason for that is basically there is at some point you need to resample the particles, and there's a good way to do that, and then there's the easy way to do that. And they use the good way, and I use the easy way. Because, we didn't really use 10,000 particles for anything anyway, so it wasn't the first priority.
Okay, thank you. Maybe you need to add a lines of code sample or a lines of code measurement or something to drive home the easy way.
All right, thank you.
Just wondering how frameworks like this compare to specialized MCMC tools like Stan. Did you look at that at all? Yeah,
so the short answer is that Stan is faster but less expressive. Okay. So if you can express your model in Stan, it will work better in Stan, but some models you cannot.
Thanks.
Hi, I really like your work. Just a quick question with the representation you have. Is it possible to detect if you are combining 2 Gaussian distributions? And I mean, often when you have Gaussian distribution, there's sort of algebraic laws that allows us to combine them in a nicer way. Is that possible to sort of do that with your current?
Well, with this representation, you cannot do that because basically whatever you have is hidden inside the lambda, so you don't have access to it. In order to take advantage of those properties of certain distributions, you'd basically have to have a richer language that would allow you to do more reflection on that. I don't think you can do it in this distribution, okay, in this implementation.
So some people already brought up part of this, namely that you need sort of a deeper embedding to actually be able to do certain techniques. You mentioned briefly, I think, during the talk that there is a way that you didn't do in the context of this paper for handling non-static conditional probability. Could you elaborate on that, or did I mishear?
Sir, I didn't hear the question completely. Did you mean the restriction that the conditioning is here and not here? Or?
Yes. Yes, that you have to have the conditioning be at the start.
Yeah, so the motivation for that is that the data you observe, the observations are there regardless of whether of whatever random choices you made, because you already know that they will be there. Therefore, from the practical...
Only for a batch computation. If it's an interacting system, you can't assume that.
Okay, so for applications that I had in mind when designing this, that was certainly the case. But as I said, this isn't really necessary. This just makes an implementation easier. And the way it's used in the sequential Monte Carlo algorithm is every time you have an observation, you basically synchronize your different threads of computation.